Let's go into a little bit about binomial distributions and how to calculate their probabilities. This is an area of trouble for some, and just kind of interpreting what we mean by binomial distribution, what are the probabilities involved, the mean and standard deviation. I'll try to keep this into one 15-minute video, see if we get it all in. Let's remember what a binomial trial is. Okay, binomial trial, have a binomial distribution. First of all, we need n trials. So we're going to, n trials are n experiments. Each one of those experiments has an equal probability of success, that's p, and all trials are independent. We're assuming that all, whether the first trial is successful or not, first experiment, has nothing to do with the second being successful, also only two outcomes. So each only two outcomes. That's the other one. In other words, heads or tails, true or false, 1 or 0, yes or no, success or failure. You get the idea. So that's why I call them binomial. Only two outcomes. The probability of success, and again, definition of success can differ from application to application. But we have a certain number of trials. They're each independent, fail or succeed independently, and each has a probability p of success. You see this big formula to the right over here. Big formula to the right, and we'll see what all that means. But let's get into an example. 4 smoke detectors each have an 80% chance of functioning during a fire. What's the probability that 0, that none of them will work, 1, 2, 3, or all 4 of the detectors work? So x is our random variable, which means that represents the number of working detectors. So let's find out. Let's first figure out the chance that none of these work. Oh, that all 4 detectors fail. Well, first I got to find out how many combinations, how many ways can I select 0 detectors out of 4? Well, there's only one way to do that. 4 factorial. If x is 0, well, 0 factorial is 1. N minus x, well, you can see this is going to be equal to 1. That's 1. This divided to 1. No real surprise there. I don't want to do that. Okay, so now I want to have the probability of success. Well, that's 0.8. But of course, x is equal to 0. And then 0.2, n minus x. Well, n minus x. Oh, so I'm letting n equal 4, x equal 0. So n minus x is going to equal 4. That's a 0, not an infinity sign. This is 4. Okay, so 0.2 to the 4th power, it's just 0.2 to the 4th power, which is 0.0016. That's the probability that none of these detectors work. Now let's find the probability that one detector works. So probability that big X equals 1. Okay, so now n still equals 4, but x equals 1. So we'll put this back into our formula. 4 factorial over 1 factorial, n minus x is 3 factorial, times 0.8, 1 success, 0.2 to the power, 3 failures. Again, so 1 success, 3 failures, 1 success, 3 failures. So 1, 3, these add up to 4, these exponents have to add up to 4. Okay, so we simply, well, 4 factorial is 24, 3 factorial is 6, 0.8 times 0.2 to the third power, and we get 0.0256. So 24 over 6, basically that's saying there's 4 ways to select one detector working out of 4. Either the first one works, or the second one works, or the third one works, or the fourth one works. That's why we divide these two and get to 4. I would say that's 0.0256, so about 2.5% chance of exactly one detector works. Okay, so we can continue this. Find the probability that exactly 2 detectors work. Now n equals 4, and x equals 2. We're getting used to this application. Okay, gotta forgive my handwriting in the meantime. This will hopefully. All right, so I got 4 factorial over 2 factorial, 2 factorial times 0.8 squared times 0.2 squared. Again, 2, 2, and 2. 2 successes, 2 failures. 2 successes, 2 failures. These add up to 4. These 2, and the denominator and the factorials, these add up to 4. Okay, so I have 24 over 2 times 2, which is going to wind up at 6. We have 6 ways of selecting 2 items out of 4, times 0.8 times 0.2, 8 squared, equals 0.1536. And we can go on. We can do the same thing for 3 and 4. So I'm going to go ahead and work those out, and then we'll return. Okay, so the final 2 probabilities, 3 successes out of 4, 4 successes out of 4, 3 successes and 4 successes out of 4. Again, 4 total, 3 successes, 1 failure, 0.8 times the power of 3 successes, 0.2 to the 1. This comes out to 0.4096. And then again, there's only one way of selecting 4 successes out of 4, 0.8 probability of success to the 4th power, and then times 0.2, the 0, again, 0 plus 4. And so 0.8 times 0.8 times 0.8 times 0.8, all of them are successful. That's 0.4096. So let's kind of recap this. Okay, so we will finish up by making listing out our distribution. So the probability of 0 successes is 0.0016. Probability of 1 success is 0.0256. Probability of 2 successes is 0.1536. Probability of 3 successes is 0.4096, and it happens to be the same for 4. Don't always assume that's going to be the case, but that's the way it works out in this case. Now, this is a probability distribution, because if I add all these probabilities up, I should get to 1, and we do. So this all adds up to 1. Okay, so that's how we can find binomial probabilities. Now, what about the mean and standard deviation of a distribution? Well, the mean and standard deviation of a binomial distribution we calculated a lot more simply than we calculated for any discrete distribution, as you might have seen earlier. Well, so the mean of this distribution is n times p. This is for a binomial distribution only, but how we have 4 detectors, a 0.8 probability of functioning, so the mean of this distribution is 3.2. Meaning that on average, if we take a group of 4 detectors, 3.2 or 80% will be working. The standard deviation That formula is n times p times 1 minus p. So that's going to be 4 times 0.8 times 0.2. That gives us the variance. We have to take the square root of that. And that happens to come out to 0.8. That's just the way it comes out. What can I say? So on average, you're going to have the number of working detectors in a group of 4 will have a mean of 3.2 and a standard deviation of 0.8. In the next video, we'll see an example of how we can find mean and standard deviation experimentally. This is how we can do it theoretically. But again, what does this number mean, this 3.2? What does this number mean, this 0.8? And we're going to see exactly what those mean in the next video.